ladies and gentlemen. We are ready to start our afternoon session. Welcome back. I hope you all had a great lunch and you're wide awake with plenty of caffeine. Yes, so you crash later. I would like to introduce John Guidi, Deputy Director of the Advanced Exploration Systems at NASA. He will be discussing NASA's Evolvable Mars campaign and the Global Exploration Roadmap. Welcome, Mr. Guidi.
Okay. Great. Well, good afternoon. I'll try to get done. I know Ralph is going to be watching me. I have to be done in 25 minutes, and that's before the insulin rush catches up with your post-lunch activities. So I work in the organization at NASA headquarters that looks at the systems we need to get beyond low Earth orbit after Orion and SLS. That's one of the things we do. We also work with our international partners, so I'm going to tell you a little bit about both those activities. There's not much time to, so I'll go a little bit fast. But starting at the top, President Obama did give us direction in the national space policies quite a few years ago to start looking at getting beyond low Earth orbit and extending humanity's reach into space. That was followed by an update to NASA's strategic goals. It's a document we use within our agency, and it helps us guide where we put money and how we prioritize funding. One of the strategic objectives, one was to put humans, advance them into the solar system and onto the surface of Mars. The phrase "onto the surface of Mars" appeared for the first time in this document formally in this last revision of the strategic goals. So this is significant for us. Another objective that showed up was the continued search for life outside of Earth across the solar system. That's also very important for us. So lastly, just earlier this year, President Obama reiterated his goal to push out into the solar system, and not just to visit, but to stay. And that's kind of a significant phrase for us. Apollo was a visitation. We had several missions there, but we really went there, got what we needed done, and then we came back, and we did it a few times, and then we canceled the program. To stay means something completely different, and it changes the way we're approaching space exploration, which I'll elaborate on in a few minutes, but it's a pretty big change for us. So internal to the agency, we have presidential approval, congressional support. We started, this is a slide we use, and it really just captures the fact that these big 4 mission directorates that spend all of NASA's monies on programs and projects are trying to work together toward getting to Mars. Science has always been the front and center organization. Human exploration was peripheral to it, but we are really trying to work together. I know we're a big agency. It's a slow boat to turn. We have had some progress, probably not where we really want to be, but we are starting to turn internal to the agency, and I'll tell you what we're doing outside of the agency in a few minutes. Of course, getting to Mars is not really a new topic for most folks, certainly not here, but for the agency as well. This is a snapshot over the past 35 years of all the NASA studies that have been done getting beyond low Earth orbit to Mars, and also external agencies, and there's been a lot, and there's some consistency in all these studies, and that is we pretty much understand what capabilities we need to get to humans to the surface of Mars and back, and by capabilities I mean like propulsion systems, keeping them alive, keeping them healthy. Those are capabilities, not necessarily the technologies that can do those capabilities. And in fact, these are the kind of the key technology or capability areas we need to focus on in the next few years. The one over there on the left is keeping the crew alive for about 1,000 days. I mean, if you have a human habitation system with a crew on board, they leave Earth, they can't come back. There's no way to come back early. They got to live for 1,000 days, and if it's 99.9% reliable, there's a bad day involved on that mission, and the crew won't like it at all. So it has to be, but we don't have that technology today. ISS is fairly intensive. We know that the distances involved will delay our communication times, and I know the crew is more or less okay with that. They enjoy being autonomous more than they are today. But if you're talking about trying to do telemedicine, and with time delays like that, it really doesn't work out, so we need to figure out how we can get around that. Over in the center of the chart, that's a heavy lift vehicle. Of course, we have to lift all this stuff off Earth. The 130-ton heavy lift SLS we're in the process of building today. We're not there yet. In the 2020s, we'll have that capability. Getting across the solar system, we plan on using solar electric power, and that's really, really efficient. It's slow, but it's very efficient, so it's great for cargo. non-human masses to get over to the Mars environment. And we're looking at the ARM mission. It's not that level power, but it's an increment toward building those capabilities. Once we do get to Mars, another capability we need to do is get through the atmosphere with a 20 to 30 ton mass vehicle. That's a lot. MSL Curiosity put down 1 ton on the surface, and it was a marvel of technology that got them there, but unfortunately that same technology doesn't scale up to that size mass. We're probably looking at retropropulsion almost all the way down to the surface, which requires a large vehicle and propellant to do that. Dropping to the bottom right, we know more recently there's a lot of water on Mars, including the lunar surface, and we can probably pull oxygen out of the water or out of the atmosphere on Mars, and it does a lot to help us landed masses, solving the previous problem if we can manufacture our own propellant or water on the surface that we can use and get the crew off the surface. That's another capability we need to do. Our scientist friends tell us, if put me in one spot, that's fine. If I can rove around pretty far, that's way, way better. So we have to build the roving systems, which have to keep the crew alive. That's probably technically easier. We just haven't built that sort of stuff at the reliability levels. The last one, you're coming back from Mars at a pretty high reentry speed. This is not too much different from Apollo. Apollo's like 10, 11, 11 and a half. But in the world of reentry, I'm not the expert, but they tell me that the heating on the surface of the reentry vehicle doesn't go up linear, like 11 kilometers a second is not 10% more than 10 kilometers a second. It actually goes up as the power of 2, 4s, and 8s. So that requires a lot more heating capability that they withstand when they come back in. So here's the capability areas that we really need to build the technology to get to. And in some cases, the technology exists. For instance, we could put humans in the Mars environment if we wanted to today. It'd take really large rockets, and several of them. We have to gang them together in orbit and push them out, but it's probably not the most efficient way. Probably looking for something a little bit more efficient with less mass. In some cases, so that technology exists there. In some cases, the technology doesn't exist, and we have to build that technology first before we get the capability. So I'm going to give you another eye chart, if you don't mind. So this is a comparison. Over on the far left, you'll see the same capabilities listed, worded slightly different and grouped together. Those are what we need to do. And over on the far right, you see a Mars surface mission. Those are the capabilities we need to do a Mars surface mission. So across the top, you see other rows, or columns rather, and they sort of list moving out from Earth toward Mars, ISS, near-term environment, going in the lunar environment, in the cislunar environment. There's a couple things we can do there. If we go to Mars orbit or the Mars moon, we need less capability. So this chart's important because it says there's lots of ways to design missions and tests to build the capabilities to get to the far right hand, a lot of ways. And it's compounded by the fact technology is not static today. We're always building things newer and better, especially in the past 20 or 30 years, things just tend to skyrocket. So we're trying to figure out what technology will be at certain points in the next 20 to 30 years for this activity and figure out what missions we need to do to build the capabilities and reliability to pull off a mission to Mars. It's going to take a long time. It's not, Apollo was 3 days there, a couple days of surface, 3 days back. ISS and shuttle were longer, but in low Earth orbit, we can come back anytime. Mars missions are 3 years long, and we need to be really good at it before we commit a crew toward going on that sort of mission. So the Evolvable Mars campaign, I'll mention that, is not really a series of missions today. It is a series of a bunch of engineers in rooms and program experts talking and trying to figure out what's the best way to achieve these capabilities over the next 20 or 30 years in the most reasonable manner with taxpayers' dollars and under some other considerations. This single chart sort of just repeats what I said. The capabilities on the left, we got approval to do this, and the Evolvable Mars campaign is trying to put everything together. But because that's just more, maybe it's too simple for us, management decided to throw some other things onto the table that we need to consider. We've been flying people for 50 years in space, and there's a lot of lessons learned. This 30-year program for Mars is going to go across a lot of political transitions. It'll be disruptive. There'll be technology advances. Science will figure out new things like they did in the past 5 years. So these are principles that we're going to use for a sustainable program. That's what we call it for 20 to 30 years. In the interest of time, I won't go through them, but maybe real quickly. The first one says, don't expect a lot of money like we got in Apollo. We'll probably just get the same money we've been getting. The second one is science and exploration work together. Humans and robots will inform each other. The third one is use really mature technology today and invest wisely in technologies of the future. The fourth one is more about we need to show steady progress in activity as an agency and maybe as a group of agencies around the world to keep continued support. The number five, the commercial activities. You know, we're just an agency. We really don't build things. We hire contractor and talent outside of the agency to get things done. And we recognize our role in the U.S. and we need to keep that in mind as we look at these systems, trades, and activities we need to do. Number six means, you know, Apollo put hardware on the surface and came back, but we got rid of everything we used at that point. We really can't afford to do that in the future. We want to use reusable systems, and once we put habitats, say, in orbit or on the surface of Mars, keep reusing them and building on them. It'll be much cheaper for us overall. The last one is going to Mars is going to be very expensive. Probably our nation can't afford it alone. We recognize that, and there's lots of talents outside of this nation that we can use to leverage in going to Mars. So this is kind of a simple diagram, but it captures all the salient points. Starting on the left in Earth orbit and ISS, we really believe we're going to go around the cislunar environment maybe for the 2020s to test out all these systems. And when we're ready, we'll plan for and pick the location that we're going to go to Mars, either on the surface, on a moon, or just orbit it for the first time and come back and build on that. The lower part, the trade space, that's sort of reiterating the Evolvable Mars campaign is an engineering study activity and analysis activity, not really a total plan. At this point, we just don't know enough to lay out the pathway that'll get us to Mars. One thing that these trades need in the engineering world is a baseline, something to compare all the trades against to figure out which ones are good and which ones are bad. The split mission concept is what we're going forward with, and maybe for those of you that might be familiar, in 2009, NASA gave a design reference architecture for getting to the Mars called 5.0. In that, it needed a lot of money to get it done, and it needed a lot of money because we thought the radiation environment from here to Mars was pretty bad, both for the crew and the cargo and the systems on board. Sensors now, like on MSL, figured out that it's really not as bad as we thought, which is great. Now we can use more efficient systems that take longer to get there, but much more efficient and cheaper, which is a good thing and kind of in line with our principles. You're sort of delaying the cost curve a little bit. So you'll see that here. About 2 years before the crew starts their journey from Mars, we'll send out and in place maybe a habitat or a rover or other systems in the Mars environment. Once it gets there and gets checked out, we'll send habitat and propulsion systems up to probably the lunar environment in orbit, not on the surface. And the crew would follow it up when it gets checked out, and they would start their relatively short journey to Mars, just much less than 12 months. Again, I mentioned we don't know exactly where we're going to go first. I'll talk about that a little bit later. But they'll do their thing there, either 30 days to 500 days, depending on the mechanics of the mission, and then they'll come back, similar time frame, 6 to 9 months. They won't go directly to Earth. We think it's best if we go back to the lunar environment. And that's so we can reuse and refurbish the habitat. And the crew would get out once they're in the lunar environment, the cislunar area, and get in Orion and SLS, launched by an SLS, and come back to Earth at that point. So that constitutes one mission. You see it takes several launches to do that. So the major results we have to date are, no matter where we go in Mars, the next few years we have to do exactly the same things to build those capabilities. So we don't need to make a decision today what location we're going to go to. We can let technology and the studies drive what makes most sense. We know ISS, even though it's in low Earth orbit, it still has a lot of value for planning getting beyond low Earth orbit, both human health and testing systems. The Earth-Moon system allows for some really unusual orbital trajectories that are pretty stable, that are easy to get into and out of, which could be advantageous when we want to get people there and send them off to Mars and bring them back. Both the Orion and SLS, there's no surprise there, were designed to support this type of mission, and they fit in nicely with the overall plan. The deep space habitation, that's probably something you'll hear more about if you want to follow human space activities. That's probably the next big system we really need to build. Orion can keep people alive and bring them back safely for a few weeks. We need something in the months, year time frame to really validate whether we can go to Mars, and we'll probably try to do something in the cislunar environment. The ARM mission has a SEP design that we think we can leverage for getting to Mars pretty easily, not SEP, and we would add a chemical stage along with the SEP for the human mission. It might make most sense to do that. The last thing is we're kind of looking at the Mars environment, not picking a location yet, but actually as a testing environment. It might make sense to send humans in orbit there and send an unmanned entry descent lander first to see how it works. It could be loaded with scientific payloads and capabilities, not sure, but we haven't figured that out yet, but we recognize Mars as a testing area as it is a destination. The plans for the next year, there's a lot. We're working in 7 different areas, basically continuing our studies. You can see in a few different areas we're looking at. Maybe the ones to point out are habitation. I mentioned that's going to be kind of important. You'll be hearing more about it. At the bottom are pathfinders, and those are sending robotic missions ahead of us to inform what the human systems need to do, and we're working with our science colleagues on defining those pathfinders today. That's probably, let me just keep going there. So I'm going to transition a little bit. So I've talked to you about the Evolvable Mars campaign, sort of how we're going to take this concept and actually implement it is when I'm now going to talk about the Global Exploration Roadmap. So quite a few years ago, a decade ago actually, a number of space agencies around the world got together and they recognized they have all types of similar challenges. They are leveraging taxpayer dollars to try and go into space. Space is expensive, it's pretty risky, and if we all banded together and cooperated, we could probably share those risks and benefits, and that sounds pretty good, and they captured in the Global Exploration Strategy, and that document was in 2007. It basically said, let's just work together, maybe we'll figure out a better way of doing business. So that's okay. It was a document that sat for a couple years and didn't go anywhere, so the same agencies got together and said, well, why don't we put some fire under it, and then they created this ISEG, the International Space Exploration Coordination Group, and those are just representatives from each of the agencies to transform that strategy into a plan. That group, coordination group, is open for any government participation around the world as long as they're willing to share what they're doing with everybody else and have open conversation. So you take 14 space agencies, government officials, you put them together, and the first thing they do is they need to create a document. So here's the Global Exploration Roadmap. They created the first one in 2011, the second one came out in 2013. And it's a document that the agencies thought would be very useful for their own agencies around the world to foster space exploration. We know that in this document you'll see words actually, in this one it's 42 pages long. You'll see words in there that recognize, previously we had science missions and manned missions. Science missions were typically robotic. In the future, they'll probably be working together, not one replacing the other, and this document recognizes that. It also recognizes that there's a lot of societal benefits. Politicians around the world take taxpayer money, most of them do, and transform it into something else, and they have to answer the same exact question, why are we giving you money for space when there's other problems here on Earth? So this group went off and did some research to say what are exactly the societal benefits of exploration. They document it here. It's not really fluffy stuff, it's actually well researched, and that's for use by the agencies, so decision makers around the world can use it to answer maybe some of the critical comments they receive. It also recognized ISS, as I mentioned, is only on low Earth orbit, but it does have a lot of capability to prepare our capabilities for future space exploration. And you might be all interested to know, everybody agrees Mars is the ultimate goal that we want to go to. For NASA, we don't want to go to the lunar surface, but most of our partners would like to go there first because they haven't been there before they go to Mars. But that's reflected in the document as well. This is not a plan either. It's not a defined plan. It's a way of facilitating coordination among the space agencies. If you don't know what other agencies are doing, you can't coordinate missions and maybe share payloads on certain things. It does have common goals and objectives, so all the space agencies generally agree on that, and some mission scenarios, which I'll show you, but it's really a facilitation tool. So 14 agencies in a room, everybody's talking about what they want to do, both robotically and human, and it's perfectly okay if 2 or 3 or 4 of them want to go off into a corner later on and make some bargains and barters. That's the role of this document, and it does it well. When those start, the responsibility moves away from ISEG and it moves to the program and projects to actually start bending metal and making things happen. Since we released the most latest version in 2013, China has gotten more active in that. I think you'll hear more about that later today. Here's a one-page version of those 40-some pages. starting off at the upper left with the International Space Station. In the middle are the robotic missions. Again, mostly science, but they inform the lower bar, which is human missions. Now this is generalized. You'll see humans to the lunar surface. So this is a document, not NASA's own document, it's the ISEG own document and reflects their desire to go to the lunar surface. This is a more detailed version of the same roadmap, and you'll find it in other parts of the GER. There's a lot more detail behind that. Last thing I want to mention on the GER, it's a living document. It's supposed to reflect what agencies want to do. As soon as it stops doing that, we'll update it. It sounds like maybe next year, the year after that, or sometime seems to be about the right time. We also recognize that governments aren't the only entities that build spacecraft and get things out into orbit. So whenever we start revising these, we have workshops around the world to try and get input from both academics, industry, commercial entities, everybody we can to try and make it a better plan. And so we'll do that next time we revise it. There's a few areas we think we're going to be focusing on in the next version. Let's see. Oh, and Mars is still the objective. So the last thing I want to mention, I've talked some concepts and maybe a document that doesn't have a lot of teeth but is facilitating. I want to point out that even today on orbit, on the ISS, there are successful international partnerships already happening. And these two gentlemen, Scott and Mikhail, are up there, went up there in March. They're going to be up there for a year because we still don't know what happens to the human body after a year in microgravity, to the neurovestibular system or even the bone loss problem. We don't know if it levels out after a period of time. There's only been a few people that have been up for a year. They're Russian, it's medical data, it's kind of hard to share. So these two gentlemen are gonna, this is actually designed so they can simulate going to Mars and figuring out what we need to do once they arrive at Mars. Are they in a state that they can operate rovers and ambulate across the surface or not, or how long does it take them to recover? Scott happens to have a twin on the ground, and they're checking genomic effects as well. I would be remiss if I didn't end with our agency's squid chart, as we call it, and it sort of reflects everything I've told you. Over on the left, we have the mission directorates working together, kind of on our way to Mars, and in the interim, there's lots of hardware and systems we need to build, and across the bottom, you'll see the Earth-reliant proving ground, Earth-independent. A lot of people say this is not reflective of that. It's Mars' secret plan to suck away Earth's atmosphere and eventually get it back to their own use. So that's all I had. Thank you. So we're open for questions, right? So I guess wait for the microphone. Mm-hmm.
I got 25 years of life, I figure, left. In your opinion, based on what you've shown, am I going to see a Mars footprint or not? Yes or no?
So I don't know. Actually, it's the 2030s is what you're talking about. Okay, go ahead.
If you don't know, and you're in charge of the whole directorate, and you're in charge of coordinating this, who in the hell does know?
So are you an engineer?
No, sir.
You're okay, because
But I know that we've had at least 50 Mars studies by my count.
okay.
And I just heard you're going to study it some more. And I'm not trying to be argumentative, but maybe a little. I had some of that caffeine.
Okay.
But come on. He doesn't write the checks.
No. Hold on a second. No, I completely feel for you. I asked you if you were an engineer because engineers go, where is the plan? Give me the plan now. But, well, so the situation is not that straightforward. I was hoping I could show why we don't have a plan today. There's technology changes that are coming up. We can't plan for 30 years of specific missions when they get thrown, some country plans for a habitat and suddenly there's a new technology that completely negates the need for that habitat. That's what we want to avoid. I'm completely with you. I would love a plan. Our stakeholders would like a plan in Congress, the executive branch, international agencies. I was sort of saying, here's why we don't have a plan in the presentation. It's really hard. We would like to do it, but we can't.
So I think my disclaimer is I work at NASA as well. I'll be talking tomorrow on in-space manufacturing and feel passionately about this. I agree with you 100%. Within NASA, what we can do, though, is we can come up with these plans. We can say what it's going to take to get there, how we're going to get there, how quickly we can get there. But it absolutely requires, through the multiple administrations between here and there, that we receive consistent funding. So that's kind of the bottom line. At NASA, we truly don't have control over that aspect. Please write your congressman.
Yes. Okay. Well, thank you for your time.